Well, good morning, folks. Welcome, everybody. Good to see you here. Happy last week of classes. Can you believe it? Has this semester, do you feel like the time can you feel the time that's passed, that's gone by, or does it feel like it's really dragged on? You feel like it's surprising we're here already? I'm curious if you can type into the chat. Does it feel like a long time, or quickest to burn out feels like forever? Hardest to finish, definitely. It feels like it's been a long time. For me, I doubly feel like it's been a long time, but it feels like, where did the time go? Similarly. It's actually kind of crazy that it's already been like 9 months since we went into shelter. Where has that time gone? That said, kudos to you for doing something useful with this time, investing in yourself and sticking with your classes. I know this has been like an insane year and a really tough semester. Not easy to kind of odds stacked against us and kind of keeping things going. So I've said this before, but let me say it again at this juncture. I really commend you and your efforts and your work in staying with it. Kudos. To give just a brief overview of what we'll talk about today, we're going to finish up the module on power. In fact, this is going to finish our material for the semester, really. I might do a little bit of, we might talk about some cool application stuff on Thursday, or maybe do a little bit of review. But for the most part, this will finish up our material for the semester. Well, it will fit this, so there won't be any further homework assignments, for one. So the one you're working on now is the last one, and this is the last material we'll kind of go over officially for anything that might be on an exam. Okay, that said, I promised I'd give you some more information about the final exam this week. And so let me do that now. I need to post this onto the, I'll put this onto the modules page shortly, but the final exam will be done at home, all of it. I was thinking about having like a kind of in-person real-time demonstration component of the exam, where you would each individually come and demonstrate. You'd check in with me on a live Zoom and I'd give you a problem to solve, and then you'd talk me through it and walk me through it. That said, given the way this semester has been, and just in general, not just in this class, but how much I'm sure you're all dealing with in terms of your coursework alone, let alone the other aspects and elements in your life. I just feel like an in-person demonstration might not be the right way to go. There was always going to be a take-home portion, but now there will only be a take-home portion. So the final exam will be take-home. I will split it into parts. I'll open the exam up next week during finals week, and you'll have most, if not the whole week, to schedule your time accordingly. And I'm actually going to break it into smaller pieces, so it won't be one big long exam that once you start it, you have to finish the whole thing, and do all of the questions, and it would be a longer time block in that sense, right? It might be like a 3-hour time block, right? This will be broken down into individual problems. So you can start any one of those problems anytime over the week, and you'll have, 25 to 30 minutes to finish that problem, something like that, or 20 to 30 minutes, depending on the complexity of the problem. Okay. So with that, I've posted a set of final exam practice problems. There's a finals module on the Canvas page now. And so you can go there for, all things related to the final. I will post some more information here shortly, namely the timing and the format of the final. And then, when I publish the exam, you'll see each portion of the final exam posted here. It'll be a separate assignment. So I've posted a set of practice problems here. These are pretty comprehensive, just heads up. So I don't want you to open this and then think, oh my God, I'm freaking out. The final exam is going to be this challenging. These are actually intended to be, they're representative of the kinds of questions you could be asked on the final, but the magnitude of them and the detail of them it actually goes into further detail than I would ask you to do within a timed final exam. So there's problems on here from kind of all of the stuff that we've done over the semester. And I will remind that a lot of the things we're doing now, the final will certainly, you'll have questions testing you on those things. But a lot of the stuff we're doing now rests on the principles we developed earlier in the course. So the, mesh and nodal analysis and voltage divider and current divider and equivalent or Thevenin resistance and things like that. Those are all things we're still using in solving, AC circuits and second order circuits and stuff like that. So even if we're working on the later material, it kind of ends up being cumulative in nature, by nature. There's no real way around that. So anyway, there's material there in the for you to practice this week. And I do recommend going through there. I haven't posted solutions to this, and I won't, but the answers are in the file itself. So on every problem, it tells you what the answers are. Okie doke. Does anyone have any questions at this time about final exam aspects? You can message me in the chat if you want, or if they come up, please do let me know and just drop me a line, or I can address it to the class. Yeah, I hope the practice problems are really helpful. If you can do those practice problems, you're in a really good position for doing well on the exam, and also, really knowing for yourself that you have met the learning objectives of the course, right? Just let's pull back for a second, go back to the broader picture. The whole purpose of this course is to prepare you for, one, to verse you in the fundamentals of electronics and electrical systems. And depending on your major, there are pieces of this class, even if you're not an electrical engineering major or a computer engineering major, which tend to, dive deeper into electronics in later courses. No matter what your major is, you're going to be using some aspects of this class. And I've mentioned before, like in civil and mechanical engineering, first and second order systems are that's a big part of what you're going to focus on, especially in civil and structural engineering. In mechanical engineering, you certainly may end up going into electromechanical systems, motors and generators and things like that. The stuff we've been talking about in terms of impedance and power, power factor and power factor correction that we're going to finish up with today, those things are really important in electromechanical systems, working with motors and generators and energy efficiency and things like that. Certainly for electrical and computer engineers, your foundations in electrical theory, Thevenin's theorem, the voltage, the resistance seen looking into a port. That stuff is super important and will come up in later courses. So we're, just all to say, if we take a step back for a second, we've gone through a lot of things and we're focused, laser focused in on certain sections. But the main takeaway is that, and this set of practice problems, if you're able to go through these, should feel really good about that, because that says to yourself that you've met the learning objectives of this course, that you are prepared for, you've got the requisite knowledge and experience and skill sets to succeed and do well in future courses and in your career. So approach the practice problems in that way. These are the things that you want to be able to demonstrate you know how to do. And if you're able to go through those and those feel good, you should be well poised to do well on the final exam problems. So Carl, thanks so much. The final will be split up into multiple small quizzes that you can take over finals week. That's absolutely correct. Thanks for asking to clarify, but that's right. And you'll kind of do those you don't have to, I don't think you have to do them in any order. I think I could do that if I wanted to, but I don't think you need to. So I think you can do it in any order you want. The lab final I'll talk about in lab today, and it'll also be next week, and it'll be take home, and it'll just be a written exam. It'll just be a conceptual written exam. On that note, big reminder, please, if you have not already, make your appointment to return your lab kit for the lab portion of the course. I'll give that announcement in lab today as well, but since we're talking about it, I want to give you the reminder that I don't know if everyone has made their appointment yet. Can you give me a quick thumbs up in the Zoom if you've already made your appointment to return your lab kit? Nice. Okay, great. That's a pretty good portion. Excellent. Okay, so if you haven't done that yet, just make sure you make your appointment. It could be the last day if you want. Remember, today is one of the days. So I think it was the 7th and the 8th, and then the 10th and the 15th. The 10th is this Thursday, and the 15th is next Tuesday. So we're getting down to kind of like the last days already. So just make sure that you're making time to do that, scheduling that. Okay, well, let's then go and pick up the discussion on power factor and power factor correction. Before we jump back into that, let's just review this last piece we talked about with both complex power and then the power triangle. Both of these concepts, one, they tie all of the different types of power together. Remember, the power triangle ties together the real power P, the real or average power actually delivered to a load or a circuit network, P, and that's the important thing, right? At the end of the day, that's what matters. Okay, and this power triangle is viewed in the complex plane. The average or real power P is then the horizontal component or the real component, right? Okay. Q is the imaginary or reactive component. I think it's labeled Q for quadrature, but that's just getting into semantics and terminology. And remember, what is it physically? It's a measure of how much power is exchanged and interchanged between the source or driving sources which remember that can always be Thevenized into like a single source, and the load. And remember that's a give and take of exchange of power or energy going back and forth. And and so it is a transfer of power between the two entities, the source and the load, but it's cyclic, and it's a continual exchange. All right, it doesn't amount to real or average power delivered from one source to the load. In other words, to actually affect, like, let's say, movement of a car, or production of sound in a speaker, or transmission of light, if it's an optical load, things like that. So so Q is the reactive power, and S bar, or S, is the complex power, which is the sort of geometric sum of those. It's equal to P plus JQ. It is a phasor. It has a real and reactive part, and it also has, there's a phase angle theta, and so it's not a yeah. So it's got a phase angle theta, and then you remember that the real and reactive powers, you can calculate those knowing the max voltage and current, and the angle that the complex power makes with the horizontal. So 1/2 Vmax Imax times the cosine of theta. Remember, you can write 1/2 Vmax Imax as the product of the RMS voltages and currents. Okay, so that relates the RMS, or effective voltages, to this real power and the reactive power, and therefore S as well. And then recall that we introduced that S could either be in the first or fourth quadrants. If it's in the first quadrant, we say that it has a positive reactive power, and we call that a lagging power factor, and that's associated with an inductive load. If S is in the fourth quadrant, it's got a negative reactive power, and we say that's a leading power factor, and we associate that with a capacitive load. All right. You can always, if you know any two of these things, S, P, Q, or theta, you can always find any of the others through right triangle geometry, Pythagorean theorem, SOHCAHTOA, and all that stuff. Right. So P is equal to S times cosine theta. Q is S sine theta. You can relate Q and P together through the tangent of theta, which we'll see in an example problem shortly. All right. Then I think we're to the point where we want to talk about power factor and power factor correction. So as we discussed at the end of last lesson, a lot of loads are inherently reactive, and their type, the way in which they're reactive is usually that they're inductively reactive. So if we go back to that power triangle, that means that the complex power associated with that load, because remember, anytime you're calculating, what is the power, it has to do with not just the source, but also the load. It's dependent on the load, right? So since a lot of loads are inductive in nature because they have windings in them, wire windings in them, for a variety of reasons, and usually related to motors or transformers. Then they have a complex power S that's in the first quadrant, and it has a lagging power factor. And keep in mind that if you want to increase the efficiency of something, remember that S is equal to, let's see, the apparent power. The apparent power S is equal to the product of VRMS and IRMS. It's what the power should apparently be. Now, if we go back and talk about the power triangle, if S is, if you're looking at my hand here in the video screen, if S is in this, has some angle, and P is only the portion of it that is, the actual power is only the portion that is on the horizontal, then the way to maximize power efficiency is to make S closer and closer to a horizontal. That is, to make theta smaller and smaller. Now, you probably can't get it to be exactly 0. But you can get this to become, much closer to a power factor of 1, that's really what that associates with, right? Power factor of 1 would be that the real power transferred to the load is exactly equal to the apparent power, right? Because the cosine of 0 is 1. Right. Okay. So then, a lot of loads are inductive naturally because they have windings in them. This could be due to motors inside the unit, or transformers, or both. If something has a moving part, chances are it's moving with an electrical motor. That includes like washing machines and air conditioners. Refrigerators use pumps to cool, move coolant through and things like that. Or move air around. Industrial loads like induction motors in electric vehicles, power tools, anything like circular a power drill or a circular saw, even reciprocating saws that move back and forth are powered with some kind of motor. It could be a reciprocating kind of action, or other things. So anyways, a lot of loads are inherently inductive, and it can behoove us to place a capacitor in parallel with that inductive load. And when you do that, you take something that is in the fourth or in the first quadrant, and you move it. You add to the power of that. You add to that a negative reactance, right? The capacitor itself, right? Q itself here has, or the inductor itself has a positive reactance. The capacitor has a negative reactance. And putting that in parallel, the two sum together. And so you can actually improve the power factor for the whole load. Okay, so here's an example, like this is just in general, a general process to figure out how much capacitance you should use to change the power factor from the cosine of theta 1 to the cosine of theta 2. So here's two different power triangles, right? One with S1, okay, at an angle of theta 1, right? And it has a reactance of Q1, right? Okay, and what we want to do is reduce, the apparent power is the same, right? So when you're adding a capacitor in there, VRMS, right? Remember that S, which is, the magnitude of this is the same. VRMS and IRMS, okay? And so, well, essentially, no, you know what? I'm sorry. I take that back. The magnitude is not exactly the same, but you are reducing the. So you're getting more power. S1 is actually bigger than S2, right? But here, then we're looking at S2, which has a smaller theta angle and therefore a smaller reactance. Okay, so essentially what that means is that S2 is closer to P. In other words, the power factor is enhanced. There's more of the power that's being generated is put towards actual power delivery, real power instead of reactive power. Okay, so the idea is what value of C is needed to change the power factor from this angle to this angle. All right, so just to outline the process, let's talk about what are the known quantities. Okay, and so we know theta 1 if we're given theta 1 and theta 2, and we know the real power P. Let's say that's all that we know. Okay, we can actually go and calculate Q1, the original reactive power. That's equal to P times the tangent of theta 1, and Q2 we could calculate, right? That's the reactive power that we need. The final reactive power we want is, again, P. The real power hasn't changed. We want the real power delivered to load to be exactly the same, is P times the tangent of theta 2. Okay, then the reactive power of the capacitor, what we really want is, we want that, Q2 is ultimately going to be Q1 minus QC, right? Or rather, it's plus the reactive power of the capacitor, except that this is going to be negative, right? This is going to be a negative Q. Okay, so if we rearrange this and solve for QC, we can see that the magnitude of QC is equal to the difference of Q1 to Q2, right? It's equal to this difference right here. Okay, and then recall that we demonstrated this earlier on the slides, but that the reactance, the reactive power for a capacitor is the square of the RMS voltage divided by its reactance, X sub C. Okay, and so this is then this is equal to VRMS squared over -1 over omega C, or negative omega C times VRMS times the square of VRMS. Okay, we have not put the J in there because Q is already a quantity on the imaginary axis, right? So we're leaving the J off because that's already accounted for when you do something like this, like S is equal to P plus JQ, right? That's already taken care of in calculating the actual, the total power there. All right, so that is really all you do. Then you find, you solve for C, right? So C then should be, again, just in our general solution here, C is the reactance, Q sub C over W omega times the square of RMS, or the square of the RMS voltage. And we know that Q sub C there is the average or real power times the difference of the tangent of the angles, of the power factor angles. Like that, that's Q1 minus Q2 divided by omega times the square of the RMS voltage. And just as a reminder, VRMS squared is equal to Vmax squared over 2. All right, so this is the general process to find out what value of C to put in parallel with the load to improve the power factor. All right. Okay. So let's take a look at an example here. Okay, and this is really similar to I think the last homework question, the last question on your homework. Okay, so it says that we've got a 120 volt RMS load. Okay, so they give us the RMS, or I'm sorry, a 120 volt RMS source. Okay, so they give us the value of the source, and it's in RMS already. They tell us the frequency is 60 hertz, and a load absorbs 4 kilowatts. Okay, a load absorbs 4 kilowatts. That is real power. It's absorbing right? It's not the reactive power. It's not the apparent power. It's the real absorbed power. It's 4 kilowatts. So we know the value of P. And we're told that it's at a lagging power factor of 0.8. Okay, so if it's lagging, that means we know that we're in the first quadrant, right, of 0.8. So that means that it's an inductive load, right? And so we want to find the value of the capacitance necessary to raise the power factor from this 0.8 that we were at up to 0.95. All right, so then in that case, then S, the apparent power, would be pretty close to the average, the actual power delivered. Okay, so to start this out, let's take a look at the power triangle here. Okay, so we know that if we start to draw the power triangle, we know that P is equal to 4 kilowatts. That's the real power. Now, associated with that is some S value, S1, and some value of Q1, right? And we want to find out what those things are. We know that we've been given the value theta 1. Theta 1 is equal to, what is it? It's 30. Oh, actually, we didn't find that yet. Let's go ahead and find that, right? So we're told that the power factor, which is equal to the cosine of theta 1, is equal to 0.8. And so we can find theta 1 just by taking the inverse cosine of 0.8, and that gives us 36.87 degrees. Okay, so we now have two elements of the power triangle. We have P and theta, 36.87 degrees. We could use the power P, 4 kilowatts, and theta to get S1, right? Just by, right triangle geometry. S, the hypotenuse, and the adjacent piece are related by cosine. But we actually already have that that we know that the power factor is also equal to the ratio of the real power to the apparent power S. And so if you rearrange this, you don't even need to use the cosine operator. You can actually just show that S is equal to P over the power factor, or 4 kilowatts over 0.8. Okay, another way to say that is that whatever the apparent power is, 80% of that is the real power. It's 0.8. Now, 80% of what gives you 4 kilowatts? Well, it's 5 kilowatts, right? 80% of 5 kilowatts is the real power, 4 kilowatts. And so we actually know that this is this is 5, and we don't write it as kilowatts. Remember, we write it as kVA. Okay, it's kilovolt amps. We call it volt amps instead of watts to distinguish that it's not real power. And then if we wanted to calculate Q1, we could do so. You could calculate this as follows. You could say Q1 is equal to P, or 4 kilowatts, times the tangent of 36.87 degrees. Or if you wanted to, you could recognize that this is the hypotenuse is 5 kilovolt amps. The adjacent piece is 4 kilowatts. And so this is a 3-4-5 triangle. So the Q is 3 kilovars. Okay, now let's go ahead and take a look at where we want to get to, we know that the power factor 2 is what we want here. And so I actually meant to, when I first wrote this over here, I meant to call this power factor 1. And in fact, let's also denote that this is power factor 1, and this would be S1 and S1. Okay. And so power factor 2, we know should be equal to the cosine of theta 2, and we've been told in this problem that we want to increase the power factor to 95%. And if you just take the inverse cosine of 95, you'll find that that gives you a theta value, theta 2, of 18.19 degrees. Okay, so our second, we can superimpose this triangle where this is theta 2, and here's S2. And we can we can calculate what we could calculate S2 if we wanted to, right? But we're not actually interested in that in this problem per se. We are interested in what is the reactive power Q2 that we need to get to, right? We need the reactive power to get to, the total reactive power to get to, well, this is going to be 4 kilowatts times the tangent of theta 2, right? And so when we put that in there, we find out that this is 1.3144 kilovars. Okay. So remember, we've been asked to just find how much capacitance is necessary to raise this power factor, to increase the power efficiency, rather, to 95%. We know that then that is a power factor angle of 18.19 degrees. The real power needs to remain the same. Remember, this load is going to, remember the real portion is associated with the resistive part of the load. And so that's unchanged. It's going to deliver 4 kilowatts, or it's going to absorb 4 kilowatts no matter what. And so so the reactive power that we need for this power factor of 0.95, an efficiency of 95% here, is then 1.3144 kilobars. So the difference then, what we need between the two of these is the magnitude of QC needs to be this 3 kilobars, 3,000 minus 1,314.4 gives us a 1,685.6 degrees, 0.6 vars. And then at this point, we can now calculate how much capacitance is needed for that. Because realize that, you know, Q1 plus, really what we're getting to here is how do we get to this Q? We're getting to this because we're going to take Q1. So Q2 is equal to Q1 plus the reactance from the capacitor. Remember that this is less than 0. Okay, it's a negative reactance, and it therefore is going to be, you know, it's going to reduce the amount of Q1. It's going to reduce the total reactance. All right. So now we just go ahead and, now that we know what that reactance is, the magnitude of it is 1,685.6 vars. We just go for calculating C. C is equal to the magnitude of QC over omega times the RMS voltage squared, and realize that that's 1,685.6 vars over omega is, well, F is 60 hertz, right? Let's just write this down here. F is 60 hertz. So omega is 2 pi times 60, or it's 120 pi. I wanted to show that explicitly so we're not confused with the voltage. The RMS voltage, VRMS, is 120 volts squared. And I think we end up with a capacitance of 310.5 microfarads. All right. Well, that concludes this session, and this is our last lesson of the semester. So we're finished up a little bit early today, and you know, if you're looking at the homework assignment here, let's see. So let's see, is this okay? So you know, here's a similar problem. You know, an industrial load consumes 75 kilowatts of power. That's real power at a 0.8 lagging power factor from a 260 volt RMS power line at 60 hertz. And what value of capacitor do you want to put in parallel to improve its power factor to 0.92? So that's really similar to the problem we just did. Here's another one. This is a little bit different. So it's a 2.6 kilowatts of power lost in a transmission line connecting a power plant to a load. So, you know, the power is generated somewhere in, let's say, your state. And then, you know, there's very long power lines, and over that length of line is 2.6 kilowatts power lost. If the load draws 170 amps RMS at 552 volts RMS, so we have the RMS voltage, current and voltage of the load, with a power factor of 0.95% lagging, find out how much power was produced by this source. So, you know, knowing this can tell you what the apparent power is, right? And if you have the apparent power and the power factor, you can figure out how much the actual power is. And so you know how much is lost in the load, and you should be able to, by, you know, the sum of the powers in the whole circuit from generator over that long transmission line all the way to the load, the sum of those needs to be 0. You know, of when you add, you know, power lost is minus, right? Or power absorbed. And then you can also find the resistance in the transmission line. Again, through, remember that power lost is going to be, you know, it's the R square of the RMS current over the times the resistance, rather. So yeah, so that concludes this this module. And we're wrapping a little bit early today. I'll stick around if anybody has questions. On Thursday, we'll look at either some you know, newer topics, or might take some questions from the practice problems. If you wanted to look at some of those, be happy to work on some of those and take a look at it on Thursday. All right, so I'm going to stop my share and pause the recording. If we don't pick up any other conversations, that'll be it for this session. And until next time.